Welcome. This video introduces dynamic memory and why it's an important concept. So to briefly review, remember that the stack is where information is stored. So all the local variables we make while we're running code, so x gets set to 10, that goes on the stack. We allocate some space, we give it a name the computer doesn't really care about, but that's our name for finding this piece of information, and we store the value to that memory location. Y takes some space, then we call a function, and that function starts just building on top of the stack and uses some space for Q and then for C. And as we finish with things, we pop them off the stack. So C, we're done with that, it goes away. We're done with this function, so Q can go away. Now we're in main. We can reuse that space that's been claimed by popping Q and C off the stack to start building up new stuff. So we use that space for Z, and then once we finish with main, everything goes away. But it's this process of continuously piling things on top of the stack, as we finish, popping them off. So with that in mind, we're going to run a piece of code. So I've got this function, getBadPointer. It makes a local variable x that's set to 10, makes a pointer to x called px that stores the address of x. Its type is a pointer to an integer, and it returns that pointer. And so down in main, I get that called getBadPointer. I take that memory address, store it as p10, which is a pointer to an integer, and then I try and print out the value that p10 points to. And I do that twice. Well, it's called getBadPointer for a reason. If I try that, it doesn't work correctly, and I get some weird results. To understand why I might get weird results, we're going to go look at that stack model. So main is started up. We called getPointer to 10, so we blast off here to start with. And back in main, we've got space kind of waiting for us for this p10 variable. So that got put on the stack, and then we go off to our function, which needs space for x, so it takes it. Needs space to store the pointer to x, which is going to have the memory address where x starts, 104. And it does all that and then returns the pointer. So it's going to return this address 104. And so that 104 comes back from the function, and we store that in p10. Looks fine. We know that if I access this memory address 104, that should take me to here. Only problem is if I run this code, it prints out and I say, okay, go print out the value at that location once, I get 10. If I say print it out again, all of a sudden I get 62, which is pretty bizarre. I print the same thing twice, the value at the address p10 points to, and I get two different answers. Well, what's happened behind the scenes is I call that cout the first time, and it goes and looks at what's currently in memory there. So it takes the address, goes off, finds the 10, and prints it out. But as part of running its code, it has to use some memory. And so it thinks that this space on the stack is now up for grabs because it was popped off when we left this function. So we just start reusing that space. And cout happens to put the value 62 in there for who knows what reason, but it does something. And it probably messes up a lot of other memory. So the second time we go to print, our address that we have no longer points to that 10, it points to this piece of memory that cout has now used for some other purpose. All right. Traditional memory, we've actually got kind of multiple areas of memory in a program. So what we're usually thinking of is the stack. And this area kind of does that growing and shrinking, and it does it actually in blocks called stack frames. But if we get a pointer to something out here on a stack frame, and that frame goes away and someone else reuses it, we run into exactly this problem. So it's not a good place to try and make some new storage inside a function because the stack is designed to give back that space and allow someone else to make use of it. there's another part of memory called the heap, or the free store, and this part of memory behaves differently. So the heap is managed by the operating system, by Windows or Mac or Linux or whatever. And the way C++ functions make use of it is they ask the operating system, hey, I would like a chunk of memory. Please give me a piece of memory out in that heap. Now the heap sticks around, and as we kind of add stack frames and remove them, nothing happens with a heap unless you explicitly say, okay, I'm done with that memory, you can have it back. Kind of the only way we would run into a problem is if you run out of memory completely and the stack and the heap collide. But unless you completely exhaust the available memory, that's not an issue. So the way we use the heap, the way we actually make this call out to the operating system and say, please give me a chunk of memory, is with the keyword new. And so in C++, C's got a different mechanism called malloc. But in C++, we say new, and then the kind of thing we want to make. I want to make an integer. And then to give it an initial value, we can use the parentheses. So this is not saying an array. This is just saying, make me a new integer and give it the value 100. And the operating system is going to get that message, go allocate a chunk of memory out here in the heap, and put the value 100 there. Now, values on the heap don't really have identifiers. We can't give them a direct name. So the way we access them is via their address. So what new does is when we call new, it allocates the space and it stores the value we want it to, and then it gives us back the memory address where that piece of information ended up. So new int is going to give us back, hey, I put that information for you at location 2010. So we can store that in a pointer. So initialize p to store that memory address that we got back from new. And then we can use that pointer to go access this piece of memory that's out on the heap. So here's the same kind of basic function, right? Get a pointer to the number 10, but this one is going to work correctly. The reason it's going to work correctly is that we're using the new keyword here. That's the big difference. The code here says to go out and make an int on the heap, so new int, put 10 there, store the address that we get for that new integer as px, and then return that address. And so we get that address back from the function, we store that as p10, and we print it twice. And this code will work exactly correctly. We'll print 10 twice. We can keep printing as many times as we want. And the reason, right, if we run this code, the kind of program starts up, p10 is allocated on the stack, and we don't have a value for it yet. We go off, we call this function. In this function, it calls new int. So the operating system says, oh, okay, I will store that for you here. Here's your address. We store that into px. So px has this memory address 2010. Now we return px back to main. So we get from this function, we get back that address 2010, and we store that in p10. And at this point, we've left this function. So where px used to be, that part of the stack has been released, and someone else can come in and use this memory again. But that's okay because we've gotten a copy of the address that we care about. And nothing is going to affect this memory until we explicitly say we're done with it. So we can print this, and even if printing messes up, cout then uses this chunk of memory, that's going to be okay because we have the address that we care about. Nothing will get to mess with this. So to release that memory, the way we tell the operating system, hey, I'm done with this thing, is by using the delete keyword. So if I allocate a new chunk of memory, I get its address, and then I do some stuff and I'm done with it, I now say delete, and I give the memory address that I want to free up the memory from. And this basically says, okay, tell the operating system, we're done with a chunk of memory that starts at 2010. It can have it back and give it to someone else. And then it's usually a good idea, if we've given up this chunk of memory, we shouldn't go play with it anymore. So we should null out that pointer and set it to be 0. so that we never even try to get back there. Now, the compiler, when we build a program, a big part of why some things happen, like arrays have to be a constant size, is because for the stack mechanism to work, where we kind of build up things on the stack and gets bigger and bigger and then shrinks back down, we have to have predictable sizes for things. That's not true of the heap. The heap, we can throw just random chunks of memory out there, and because we don't have to worry about this kind of gracefully resizing, we can have arrays that are on the heap that are any size we want. They can be based on a variable. So I can create an array on the heap just like I would a normal array, make me an array of ints, but we have to use this new keyword, and we don't give it a name. So this says, make me an array of this size, list size, of integers, and do it on the heap. Right? That's the new keyword. And once again, we're not going to have any name for this array. What we're going to do is we're just going to get its memory address back and store that in this pointer called nums. Right? We'll have the memory address of this array. In list size here, this is a variable which for a normal array would not work, but as soon as we use new, we're putting it out on the heap, and this is allowed. And you may remember from the arrays section that an array and a memory address, an array, when we talk about an array, we're really just talking about a memory address, that base address where it starts. So we're allowed, if I have a pointer like nums, we're allowed to kind of go the other way and to treat that pointer as an array. So even though nums is technically a pointer to an int, I can just start using it like an array. So the book example for returning a dynamic array, this is how it works. We've got the main function. It creates a list of numbers, 1 through 6, and then we call this reverse function, and we pass it the array, and we pass it the size of the array. So the reverse function takes in a memory address, which is what an array is. It's constant, so we're not going to mess up that one, and the size. We use that size to make a new array of integers with size 6 in this case. So we throw that out in the heap. We get the memory address back from new, and we store that as a result. And we can use that memory address as the base address for an array and just start indexing into it to copy things from list to result. And so we just go kind of piece by piece, and we've got I is indexing to the original list, and it's counting 0, counting up until we hit the size. J is starting at the size minus 1, so we're counting backwards. We're counting down until we hit 0. And we copy from the front of the list to the back of the result of this new piece of memory that we created that is holding an array of integers. And when we're done, we return result. We return this memory address, which we can store as reverse list. And then once again, if we want to print it out, we just pretend it's an array. We know that it's an array. We know this memory address points to an array, so we just start using it like that. Now, the one danger on something that we'll deal with a lot in 162 is when we start doing this, we start creating things on the heap. If we never free up the memory, we can create what's called a memory leak. So I make a new big list of integers, and it takes up a whole bunch of memory. And then I store that address in nums. And then I run this next line of code that says, okay, make me a new list of integers, a new array, and store its address in nums. So we make the new thing, we get its address, and we store it in nums. Well, we still own this chunk of memory, but we've forgotten its address. That's what a memory leak is. You own a chunk of memory, and you don't have its address, or maybe you have its address and you just are sitting on it. But we're not getting rid of, we're not freeing the memory that we own once we're done with it. So to do this correctly, you have to, when you're done with a piece of memory, you create this array, you do some stuff with it, you delete, and then use the brackets to say delete the whole array, nums, and free up that space so that's available for someone else before you go create a new chunk of space. When programs fail to do that, they start taking more and more and more memory and eventually slow down and possibly crash. You may have witnessed that yourself in some program. Now, when your program exits, it's going to free all the memory, so it's not like you can steal memory and then your program closes and that memory's gone forever. You can only leak memory while your program's going, and then once your program closes, the operating system automatically reclaims all the memory your program was given. But it's still not a bad idea to get in the habit of freeing up memory. Doing this for a complex program is very tricky, and this is why real programs have memory leaks. It's the kind of thing that people are really bad at. And we'll talk about in 162 the mechanisms we use to effectively manage the memory that our programs are creating and freeing.